Hello, welcome all for this particular new topic which I am taking up in today's session. The name of this particular concept, what I'm trying to discuss in today's session, is infrared spectroscopy, or we also call it as IR spectrophotometry. And myself, Dr. Girish Hampanava, Assistant Professor, KLA College of Pharmacy, Vidanagar, Hubli, will be discussing with infrared spectroscopy in these coming episodes. So, first going through the introduction of this infrared spectroscopy. So, as we have seen, the ultraviolet and the fluorimetry both are used for analysis of the structure of a chemical compound. So, similarly, this infrared spectroscopy is also used for structural analysis. Maybe any compound which is organic or inorganic in nature, or almost any compound that has covalent bonds, whether organic or inorganic, and which absorbs various frequencies of electromagnetic radiations in the infrared region of electromagnetic spectrum can be analyzed in this particular technique. The second thing is it can be used for both qualitative and quantitative analysis. So what we mean by qualitative analysis is the compound or any organic compound, if you are determining the kind or the nature of that particular compound, then it becomes the qualitative aspect. If you are determining the quantity or the amount of that particular compound in any given component, then that becomes a quantitative analysis. So this technique can be used for both qualitative as well as quantitative analysis. So this infrared spectroscopy is basically based on the fact that chemical substances, they show selective absorbance in the infrared region of the electromagnetic spectrum, and after absorption these molecules tend to vibrate because their vibrational frequencies will match with this electromagnetic radiation frequency, and they tend to vibrate at many rates of vibrations, thus giving rise to a closely packed absorption bands, and we call these absorption bands as IR absorption spectrum, and this may extend over a wide wavelength range. Okay, similarly, as like we had in the UV visible spectroscopy, the compounds which are having either double bonds or triple bonds, or which are rich with electrons in rich with electronic configurations, they were usually sensitive to UV radiations, and these electrons were taking up the energy, high energy, and they were getting excited to the excited state, and that was the principle what we studied in UV spectroscopy. Similarly, this infrared spectrum is a sort of absorption spectrum as like ultraviolet spectra, where in which the molecules will tend to vibrate at a particular frequency of this infrared electromagnetic radiation, and because they tend to vibrate at that particular frequency, because their fundamental frequency will match with the incoming electromagnetic radiation, that is the infrared radiations, that absorption of the radiation will give to this absorption bands. We call them as infrared absorption spectrum, and that happens over a wide wavelength region. We will see which over what wavelength region this absorption really happens. I will show you the wavelength region of this infrared spectrum in this particular slide. As you can see here, we had already discussed about ultraviolet and visible spectroscopy in the previous two sessions, where we discussed ultraviolet as well as the fluorimetry, and the particular wavelength region for these two electromagnetic radiations was starting from 190 or 200 nanometers up till 800, nearly 1000 nanometers. So practically we were defining them as 200 to 400 for ultraviolet, and from 400 to 800 for visible. So this visible radiation is of longer wavelength, whereas the ultraviolet radiation is of shorter wavelength. When I tell shorter wavelength, they usually have the higher frequency and higher energy. So I would like to bring your attention to this entire wavelength region here. As I travel towards my left, the energy increases, whereas the wavelength decreases. As I travel to my right, the wavelength increases, whereas the energy decreases, and the frequency also decreases. So, in this particular concept of infrared spectroscopy, we are dealing with the next portion in the electromagnetic spectrum, that is the infrared spectrum. We can see NIR, MIR, and FIR. These all three regions, which are lying in the very neighborhood of this visible red end of the visible spectrum, they fall under the category of infrared regions. Okay, I'll come to this part NIR, MIR, and FIR in the very next slide. So, if you want to see the demarcation or the wavelength demarcation for this ultraviolet and visible wavelength region as well as the IR region, you can see the ultraviolet or the visible region ends at 800 nanometers, and the place where it ends, or the place where the ultraviolet and visible region ends, from there the infrared spectrum region starts. So basically it means, as I mentioned previously, if I travel to my left, it is high energy region. As I travel to my right, it is the low energy region. So compared to visible radiations, the infrared radiations are less energetic in nature. So since they are less energetic in nature, these infrared radiations do not bring the same kind of changes what ultraviolet and visible radiations were bringing about. I mean to say, these infrared radiations cannot bring about any electronic changes what we used to see in UV visible radiations. These infrared radiations will not bring about any any electronic changes, but rather there is an important observation: they bring about vibrational changes. And throughout this discussion, we'll be discussing about the infrared spectrum, which is also known as, we also call this MIR in particular, we call this as a vibrational portion of infrared region, where this particular wavelength region, that is from 2500 nanometer to 25,000 nanometer, this particular region or the mid-IR region, I'll come to this in the very next slide. This particular region is practically much applied, wherein which we call this as a vibrational portion in the infrared spectrum. So we tend to use this MIR region for analyzing our organic or inorganic molecules, and usually if you convert it into the wave number, this MIR region will be demarked as 4000 to 400 centimeter inverse. I will come to this change in the units, as well as why do we use wave numbers rather than wavelengths. As far as in the UV visible discussion, we used wavelengths, that is 200 to 800 nanometer, which was nothing but the wavelength region. But in this particular discussion, we will not be using the wavelength, rather we will be using the wave number, which is the 4000 to 400 centimeter inverse. I will come to the reason for why we shift from wavelength to wave number in this particular discussion in the coming slides. So this was about the region or the wavelength region of infrared spectrum, and as I mentioned, this infrared spectrum starts just after the red end of the visible region. So the wavelengths of the infrared radiation of interest to chemists trying to identify or study organic molecules, they fall between 2.5 to 15 micrometers. Now the unit again has changed to micrometers. This 2.5 to 15 micrometer is nothing but our mid-IR region. Some chemists, they usually make it 2.5 to 25 micrometers. So the IR wavelengths are longer, as I have just now mentioned, because as I travel to this right end, then the wavelength will tend to become longer and longer. As the IR wavelengths are longer than those in the red end of the visible region, which is generally closer to the end at about 0.75 micrometer. So in the coming slide, I will show you here, which is the near IR region, which starts from 0.75 and ends up to 2.5 micrometer. And the mid-IR region will start from 2.5 and ends up to 25 micrometer. And the far infrared region will start from 25 and ends up till 200 micrometer. I will come to this discussion right after this slide. The IR radiation is of lower energy than visible radiation, but of higher energy than radio waves. So the radio wave is lying right at the right side of this infrared region, and on to the left of this infrared region is a visible region which is more energetic compared to the infrared radiations. As I mentioned, I would like to bring your kind attention to this particular diagram here, where I am demarking the region of the entire IR magnetic radiations or electromagnetic radiations in three different categories, that is near IR, mid IR, and far IR. And the demarcation is from 0.75 to 2.5 micrometer for near infrared region, and from 2.5 to 20 micrometer, 25 micrometer, it is the mid IR region, and from 20 to 200 micrometer, it is the far IR region. I am still using micrometer, which is the wavelength. And as I mentioned, the vibrational portion of the infrared region, which is nothing but the mid IR region, is practically more applied in terms of spectroscopy. In the next slide, I have a chart where I have tried to show what for these three regions are more applicable, and as a chemist, which region is more useful to us. So the IR wavelength range tells us the IR frequency range from this equation. We know that we have studied this equation right in the very beginning of the UV visible spectroscopy, where the wavelength is inversely proportional to wavelength, which is nothing but the lambda, is inversely proportional to the frequency, which is nu, and is governed by the relationship nu is equal to c by lambda, and where c is the speed of light, and this nu is the frequency and lambda is the wavelength. So it is, as I mentioned, it is common to use wave number. We take not the wavelength but the wave number throughout this discussion of infrared spectroscopy, because most of the chemists would rather prefer to the radiations in vibrational infrared region of electromagnetic spectrum in terms of unit, which is wave number, rather than wavelength. Wave number is expressed in terms of nu bar, and wavelength, which was expressed in terms of micrometer or mu. So it is rather a convenience, and also there is one more reason why we usually use the wave number rather than the wavelength, is because the wave numbers as units is that they are directly proportional to the energy. Okay, this you will understand if you see 2.5 and 25 micrometer, which is nothing but the wavelength, and 4000 to 400, which is nothing but the wave number. In terms of the magnitude of this number, or in terms the higher the wave number corresponds to the higher energy, I mean to say 2.5 or 4000 centimeter inverse, which is the wave number, since it is higher than 400, it can be directly correlated, or it can be directly taken, or it is more convincing that 4000 is more than 400 and 4000 is more energetic than 400. In order to have that sort of understanding, most of the chemists try to shift to the wave number but not the wavelength in this particular infrared spectroscopy. So as I mentioned, this wave number is represented by nu tilde and also as nu bar. Both the symbols are used in the literature, whichever textbook you refer to, both are used in the literature. And the unit centimeter inverse is the reciprocal of the centimeter. That is, what we had was, if you express this wavelength in centimeter, and if you take the reciprocal of this 1 by lambda, then the wave number will be having a unit which is centimeter inverse. So the wave number is the number of waves of radiations per centimeter, which was already discussed in the visible spectroscopy. So the frequency is the number of waves per second, which we also know that, and you can interchange the wavelength and wave number by this particular equation, where wavelength in micrometer times wave number, which is the centimeter inverse, is equal to 10,000, or it is equal to 1 times 10 to the power 4. In order to identify, if you have the wavelength, if you want to convert it to wave number, just rearrange this equation. Like wavelength is equal to 10,000 divided by any wave number which actually you have and which you want to convert it to wavelength. Similarly, if you have wave number, you can convert into wavelength by using this particular formula. So don't be worried if you have any wavelength, how can I convert it to wave number? It is so simple as it is by using this equation. So as I mentioned previously, I said I will be telling the usefulness of all these regions which fall under the category of infrared electromagnetic spectrum, which is demarked by this particular three regions. The first one is near IR, mid IR, and far IR region. As I mentioned, it is 0.7 to 2.5, 2.5 to 25 micrometers, and 25 to 1000 micrometers, which is nothing but the wavelength. But as I mentioned, we don't use the wavelength as a unit in the entire discussion. We rather prefer to use wave number, and if you convert these values into wave number, you can see the 14,000 is rather more energetic compared to 4,000. I mean to say, the energy is increasing if I go towards my left on this screen. So the mid-IR region, as I mentioned, is the vibrational region or vibrational portion which I am very much interested in, and throughout the discussion we are taking up this mid-IR region, and we also have the far IR region, and this far IR region will be overlapping with the microwave radiations. So it is like not the clear-cut demarcation between these electromagnetic radiations, but there is a sort of overlapping. The red end will be overlapping on this near IR region, and the microwave region will be overlapping on this far IR region. So coming to the applications of this near IR region, mid IR, and far IR region, all of them are used for analysis, but as I mentioned, it is mostly the mid IR region which is sufficient enough for analyzing all the organic or inorganic or polymeric compounds for what we have in our on our shelves. So coming to the near IR region, analysis of organic compounds, and we can analyze all the organic compounds here which are in the liquid form or the solid form, and we usually use this near IR wavelength or wave number region for quantitative analysis of some well-known objects. Coming to the mid-IR region, this can be used for both organic and inorganic and some polymeric compounds, and it can be used for all the three states of samples like liquid, solid, and gaseous, and it can be used for both qualitative as well as quantitative analysis. So this is the often used and most characteristic wavelength region, which gives a lot of information about any given organic molecule or inorganic molecule or any molecule that has a covalent bond in it. Okay, so the covalent or double bond or triple bond in it. So this mid-IR region is semi-non-destructive. I mean to say, the sample analysis is semi-destructive or non-destructive kind of thing, where we literally do not destroy our sample, rather we can conserve it back as it is not totally destroyed during analysis. And this far IR region, as I mentioned, it is rather used only for inorganic compounds and mostly the solid compounds, and used for qualitative and semi-quantitative analysis, and also this method is semi-non-destructive kind. So coming to the kind of spectrum that is visible once after we perform this infrared spectroscopy technique. So the band intensities, the kind of graph we get after analyzing the infrared spectrum, they somewhat look like this. Okay, so there are two different kind of spectrum what basically we get out of this infrared spectroscopy, and the band intensities in the infrared spectrum will be expressed as transmittance or absorbance. As I mentioned, it is the absorption of the infrared radiation in the very beginning, but we can also take the transmittance as we can correlate the absorbance with transmittance with this particular formula. So we end up ultimately having two different kind of absorption spectrums, where the plot is plotted versus wave number on x-axis and absorbance on y-axis, or it could be also percentage transmission on y-axis. So the y-axis is variable. We can either take as percentage transmission or we can either take as absorbance. So we all know that the transmission is the ratio of the radiant power transmitted by the sample to the radiant power incident on the sample. So it is the transmitted radiation. It is the ratio of transmitted radiation to the incident radiation, and that is what we call it as times 100. We call it as transmittance, and absorbance is the logarithm to the base 10 of the reciprocal of the transmittance. So we can interchange the absorbance and transmittance. That is simple mathematics, and thus we end up having these two kinds of spectrums or infrared spectrums. Just to have a look on this x-axis, it starts from 4000 and ends up till 400. As I mentioned, 4000, as I travel towards 4000, it is high energetic region. As I travel towards 400, it is low energetic region. And most of the chemists, to mind you, they rather prefer transmittance spectrum, which is the above one, rather than absorption spectrum. They are more convenient in handling the transmission spectrum. And if you can see, the transmission spectrum, the y-axis starts from 0 and ends up till 100. And that is not the same with the absorption spectrum. It may start with 0 and it will end up with 0.45 kind of reading. So, because of the convenience, simple mere convenience, they rather would like to prefer the transmittance spectrum. So I start from 400 and I end up till 4000. You can see this scale is non-linear. I mean to say, the scale has been fused just to fit the since there are no observation in certain regions. If you see from 2000 up till 2800, you don't see anything major. Rather, what they do is they prefer to condense this particular region. So that is just simply a practical reason to accommodate all the peaks on a small screen. And because of this wide wavelength regions, wave number regions in the infrared spectrum, we tend to collapse this horizontal scale, and frequently it is a non-linear scale. And I have taken an example of a comparison of the same molecule, or it is the same molecule which has been taken as a transmittance spectrum and an absorption spectrum, so that we can correlate both. So the intensity of the IR radiation absorbed or transmitted is plotted on the y-axis, as I just now mentioned, against the frequency or the wave number of the radiation on the x-axis. So we rather prefer wave number on the x-axis and the percentage transmission on the y-axis. When infrared radiation is passed through a sample, the frequencies corresponding to the active vibrational modes of the molecules of the sample are to some extent absorbed, while the other frequencies are transmitted through the sample without being absorbed by the sample. So the reason of this whole statement is, when you subject a molecule with the infrared radiation, if that molecule has some portion in it which corresponds or which responds to the incoming frequencies or incoming infrared frequencies, then there is a resonance that happens. Not all the functionalities in a molecule, or not all the function group in a molecule will show the absorption at once, but rather they show absorbance of the incoming frequencies at certain wave numbers or at certain wavelengths. Not all the functionalities in a molecule will show vibration at once, but rather they tend to show the vibration at their corresponding frequencies, and once they match these incoming frequencies, they tend to vibrate. And whenever they tend to vibrate, we say the sample has absorbed the infrared radiation. And the absorption intensity depends on the probability that the infrared photon energy is transferred to the molecule. The intensity of the absorption band is proportional to the square of the rate of dipole moment change during the vibration. I will come to this, the dipole moment and the absorption of infrared radiation, in very detail, as it is a very theory of this particular concept, and we will understand what is the need of change in the dipole moment and how it responds to the incoming infrared photon energy, and how that energy is transferred to that particular molecule, and how that molecule will tend to vibrate by taking up that particular energy. And that's how we say that the molecule has absorbed the infrared radiations. Radiation of various wavelengths can be absorbed depending on the chemical composition of the sample. As I have just now said, radiations of various wavelengths, not one wavelength can be absorbed. I mean to say, one molecule if it is having two different functional groups like OH and COH, this OH and COH will not vibrate at the same wavelengths, but rather they have their own specific wavelengths where they tend to absorb the incoming infrared radiations, and that's how they tend to respond to those particular wavelength regions, and we say the energy has been absorbed. And coming to the principle of IR spectroscopy, before I go on to this, the principle of IR spectroscopy, the absorption of infrared radiations cause an excitation of molecule from lower to higher vibrational energy levels. So we have a new concept called as a vibrational energy level. So when we were discussing the electromagnetic radiations, or the fundamentals or the basics of electromagnetic radiations, we saw that we had four different energy levels were existing, that is translational, rotational, vibrational, and electronic energy levels. And the energy of these uh, vibrational levels were different, and the electronic energy was the highest energy needing vibrational energies, whereas the vibrational was a bit less compared to the electronic, and rotational was a bit still more or less compared to the vibrational, and translational we neglected because it is happening in the gaseous state. So absorption of infrared radiation, it can only afford the vibrational energy changes, and this causes the shift of this particular, or the state, it will change the state of the molecules from the rotational, I mean to say one vibrational energy level to the another vibrational energy levels, and that happens only after the absorption of infrared radiation. As like in ultraviolet spectroscopy, if I refer to this particular diagram here, in ultraviolet spectroscopy it was the electronic state that was involved, and electron here was taking up the energy and going to the excited state. So here the infrared radiation absorption of the molecule, what happens is these electronic changes are not visible. I mean to say these electronic changes won't happen, as because they need more energy, and only ultraviolet radiations can afford this electronic changes. But higher radiations or infrared radiations won't afford this electronic changes, but rather they afford vibrational or rotational energy changes. So if you see, we have one vibrational energy level, and the other, and the other, and the other one. So we have several vibrational energy levels. In order to achieve this, the jump from lower to higher vibrational energy levels, a molecule should absorb the infrared radiations. Once after absorbing the infrared radiations, the molecule will tend to go from lower to higher vibrational energy levels. And if IR wavelengths are longer than 1000 micrometer, the absorption will cause the excitation to the higher rotational states. I mean to say 1000 micrometer is the very least energy, and it falls in the category of far infrared region, and that far infrared radiation can only afford rotational changes because that has very less energy compared to the mid IR region or near IR region. If wavelength absorbed is between 1 to 100 micrometer, the molecule will be excited to higher vibrational states. So I was mentioning, we rather say this as 2.5 to 25 micrometer, as I mentioned, which is a vibrational portion. The radiations within this wavelength region are the one which brings about the vibrational changes. The energy required to cause a change in the rotational level is small as compared to the energy required to the vibrational level change, which I just now mentioned, and each vibrational energy is associated with number of closely spaced rotational energy levels. As we had, each electronic energy levels were associated with the closely spaced vibrational energy levels. These vibrational energy levels, for example, this and this vibrational energy level will be having closely spaced rotational energy levels, which I mean to say these lines. So if you want to achieve these rotational changes, we don't need any more energy, rather the longer wavelength region can be used to achieve the rotational changes. If you want to afford the vibrational changes, then we want this vibrational frequency region that is from 2.5 to 2.5 to 100 micrometer, which is falling under, or we can use either the near, mid, and far infrared regions to afford this vibrational changes. So Therefore, in the gas spectra or in the gas phase, the IR spectra are of discrete lines because of rotational changes. So, in the gaseous, if a sample is present in the gaseous form, if you take an IR spectra of that sample in the gaseous form, we tend to visualize the discrete lines. That discrete lines is because of the rotational changes but not the vibrational changes. Whereas the condensed phase or the liquid or the solid samples, if you take an IR spectra of this, we tend to have a broad absorption bands. That is because of the vibrational changes. That is the reason I would like to show you the two spectra where, yeah, this is the one where I have taken an example of hydrogen chloride, which is in the gaseous form. And if you see the spectra, which is because of the rotational energy changes, the peaks are very sharp and they are very much clear or distinct from each other. And whereas if you take the condensed phases, the spectra tend to broaden. As you can see, the spectra of the condensed or the solid or the liquid state, the spectra will tend to broaden like this. So that is the reason, because of the vibrational energy levels, this spectra will broaden, whereas the rotational spectra will tend to show these sharp peaks. And that was the comparison what I have made between these two samples. The first one is the spectrum of hydrogen chloride, which was taken in the gaseous phase, and the second is the broad vibration spectrum of a film of polystyrene, which was taken in, uh, in this particular condensed phase, and that was because of the vibration changes. And IR spectroscopy is also termed as vibrational rotational spectroscopy. So you should be also aware that the infrared spectroscopy is called as a vibrational rotational spectroscopy, as like ultraviolet spectroscopy was called as electronic spectroscopy. This is also this is also called synonymously by this name, that is vibrational rotational spectroscopy. And the IR light is absorbed when an oscillating dipole moment interacts with the oscillating electric vector of an IR beam. This is a very important thing. Rather, I can say this is the core theory or the principle behind this particular infrared spectroscopic section. So I will discuss this in very detail in the coming slides, but I would like to give a gist before I end up this particular session. IR light is absorbed when an oscillating dipole. So, for a molecule to be IR active, a molecule should have a dipole moment. And because of this dipole moment, there tend to be an oscillating dipole moment which generates out of this molecule which is having a dipole character. And that isolating dipole moment which is generated from that molecule, that tend to interact with the incoming radiation, which is nothing but the infrared radiation, and in particular the electric force field. As I mentioned in the very discussion, that electromagnetic spectrum is the alternating force field of electric and magnetic force fields, and this IR radiation is also an electromagnetic radiation, and the electric vector of this incoming electromagnetic radiation will interact with this oscillating dipole moment, and that's how they couple. And that coupling of these two radiations, we call it as the absorption of electromagnetic radiation, that is IR radiations. So with this introduction, I would like to end this particular concept, and in the next session I would like to discuss with respect to the requirements of an IR, what are the requirements for any molecule to show IR absorption. This will be the discussion or the topic of discussion for the next session. Thank you for listening, and shortly we'll be receiving another session about this IR spectroscopy. Thank you very much.